screen visible?
Yes.
Okay. Yeah. So since there are very less number of people, I'll keep it very interactive. Okay. So did you all go through the previous discussion that I have done? I think Mayuresh and Sampit that joined the previous discussion. Anna, did you go through the previous discussion that happened like last week?
Yes.
Okay. Fine. So today we'll be dealing with one of the most important tensor quantity. So the entirety of general relativity can be like said that its main idea is to find out the metric tensor. And if you know the Einstein's field equation, the aim of the field equation is to solve for the metric tensor. And once you get the metric tensor, you can find out all the other properties of that particular curved space. So that is the reason metric tensor is one of the very important tensor that tells about how the it actually represents how coordinate axes are dependent on each other. Okay, so to arrive at metric tensor, I'll go through few logical reasonings. Okay, so now if you see any coordinate system, what will come in your mind? You will see some coordinate lines, you will see axis, and any point in that in the space can be represented by a n tuplet, right? Like you can write x1, x2, x3, so on. Depending on the number of dimensions, there will be those many variables, right? So now in any coordinate system, we will also see the coordinate axis, right? So what is the simplest two-dimensional axis that you guys know?
Cartesian axis.
Yeah, so it is the Cartesian coordinates. So basically, first thing that we will draw is the coordinate lines, right? So this is the x-axis and this is the y-axis. Any point is represented by x comma y, right? Any point is represented by x comma y. And how will you get this? So in flat space, either you can take, so if this is the vector, the position vector of this point, either what you can do, you can take dot product of this r vector with x direction. That is r vector dot x direction, I'll just represent it by ex vector. That gives you x component. So this type of getting the component is called as the covariant component. I discussed this in the last discussion also. So this type of getting the components is called as the covariant component. But the other way is, so if you want the x component, go parallelly in the direction of y-axis. So like this. So you'll go parallel in the direction of y-axis, and then it intersects. So this gives you one value. So even that is a component of this r vector. But that component is called as the contravariant component. So basically, it will be easy for you if you see like non-orthogonal coordinate system, somewhat like this probably. In this case, what you can do? Either you can take perpendicular to the axis and get a value covariant component, or you can take this kind of cut and this value gives you the contravariant component, and this gives you covariant, right? So I discussed this in the last class, so go through that if you have any doubts. So did you guys understand this idea? How do you get actually contravariant and covariant component?
Yes.
Okay, fine. So now what we will do is I'll define something called as the displacement like the quantity called displacement, okay, ds. So what does this say? In any arbitrary curved space, okay, the distance between two very close points, I'll call it ds. Okay, so it's just like the line element or the that gives you the information of distance between two closely related points. Okay, so this is ds. Now how do you get actually this ds? So you can draw a position vector, right? So say this is r vector, then this will be some r vector plus dr vector. In that case, this distance I can write it to be, or the distance between two points is dr vector. So this is simple vector, a geometrical way of getting distance between 2 points. So basically dr vector is, so if I write it to be r1 vector for the initial one, and the second one to be r2 vector. So in that case, dr vector is r2 vector minus r1 vector, right? Isn't it? So the magnitude of this dr vector is called as ds. So magnitude of this dr vector is called as the ds, or the displacement between 2 points. Now this ds is a invariant quantity. It's a scalar. So if you see this displacement in any other coordinates, for example, for simplicity, consider this Cartesian coordinate, and you have some ds here. Okay, this is ds. But if I rotate these coordinates in this manner, still this ds value will not change, right? So even in the rotated coordinates, this ds value won't change. But what will change? It is the component of this r1 and r2 that will change. But ds as a quantity will not change when you change the coordinate system. So that is why this ds, or the displacement, is an invariant quantity. Okay. Now, how to mathematically get the equation for ds? So we know that r vector equal to, so in component wise, how can I write r vector? Usually in Cartesian, how we can write it to be x I cap plus so on, right? So in any arbitrary coordinate system, I can write r vector to be x1 in e1 direction plus x2 in e2 direction, goes on, right? So this in Einstein notation, I can write it to be xi ei vector, right? So this is your r vector, where xi is your contravariant components. Okay, so if this is r vector, I can also write r vector to be, so this I is a dummy index, isn't it? So it doesn't matter if I write I or if I write j. The only constraint is the superscript of x and the subscript of e vector should be the same. So I can write it to be xj ej. It doesn't make any difference because it is just summed over, isn't it? So now what I will do, I will write r vector dot r vector. So now what will happen? I'll write for the first r vector, I'll write the above value, that is xi ei dot xj ej. So I can do this, but do you think I can do xi ei uh, in the both terms? Here I wrote in different index, but can I do it in the same index? Guys, are you here? Myresh, Sampreet, Anand. Am I audible, guys?
Yeah,
Yes.
Sagar, you're audible.
Yes.
Okay.
Just repeat the question again. Maybe they didn't understand.
Okay. So my question is, in this expression, I wrote xiei dot xjej. Right. So is it possible for me to write xiei dot xiei again? Like, is this possible? Xiei dot xiei.
Are you guys here or Anhad, Mayuresh, and Sampreet?
I don't think we can write it that way.
Okay. So why can't we do this?
Because that would only give the components in one particular direction as a dot product. So it would be x1 dot x1, but we wouldn't get x1 dot x2 if we write it like that.
Yeah. So basically, if we write r vector as x1 e1 plus x2 e2, like just for simplicity, I'll just keep two components. Now, if I want to do r vector dot r vector, then what I can do, I'll just write this 2 times and multiply, distribute. So there I'll get x1 square e1 dot e1 plus x2 square e2 dot e2. But there will also be cross terms. There will be 2x1 x2 and 2x1 x2 e2 dot e1 or e1 dot e2, right? So if I write it to be this manner that I'm showing here in red, so if I write it like this, I'm not accounting for the cross terms at all because I'm using the same index. So that is the reason I have to use different index. And there is also another rule in tensor. In one particular term, a particular index can appear only twice, like one in superscript, one in subscript. It can't appear like both in superscript. So if both appears, it is invalid. And also, it can't appear 3 times, right? So that is the reason one index can appear only twice maximum in a particular uh, term. Okay, so that's a handy rule that to keep. So fine. So if I expand this expression, so what will I get? R vector square is equal to xi xj ei vector dot ej vector, right? Now we know that this value may be 0 or may not be 0, right? Depends on the coordinate system we are talking in. So for example, if you are talking in orthogonal coordinates like Cartesian, here obviously when I is not equal to j, like in 3-dimensional Cartesian, when I is not equal to j, then this value will go to 0 in orthogonal coordinates. But there can be coordinate system with which need not be orthogonal, something like this, right? Some coordinate system like curvilinear coordinates or some curved space, it need not be 0 always. So in that case, this will always not be 0, right? So that is why we can't just neglect it. Now I will just name this ei.ej as gij, I'll explain the physical significance of this. But this Gij is called as the metric tensor component. Okay. So this will give me xi, xj, gij. Okay. So this is r square. Now in Cartesian coordinates, you guys know that what is r square value in Cartesian coordinates? That is x square plus y square plus z square, right? So there are no cross terms at all in r square expression. So what does it say? Only when I is equal to j, I can do xi, xj, right? So it implies it will be equal to xi square, right? But if I is not equal to j, it will be 0. Xi, xj will be 0. So this quantity, you all should be familiar, it's called as the Kronecker delta, right? So we can relate this to the Kronecker delta, where I can write r square equal to xi, xj, delta ij, where gij equal to delta ij. For what coordinates? It is true only for Cartesian coordinates. So for Cartesian coordinate system, we know what is the metric tensor. It is just the Kronecker delta, or this identity metric or identity matrix. This is the metric tensor for Cartesian coordinates. But for other coordinates, it will not be just identity. For example, if you see this polar coordinates, I think if you had solved the assignment, you will get to know that for polar coordinates, the metric tensor is 1 r square sine theta, and the other terms are 0. So this is the metric tensor for polar coordinates. For cylindrical coordinates or 3D cylindrical, so there it will be. So I'll use the variables rho, phi, and z in cylindrical coordinates. So for this cylindrical coordinates, my metric tensor is 1, 5, okay, rho square and z. So if you go through the assignment, I have given an expression how to calculate g, but I think I'll just give you how it is. I'll show you how that expression came. Okay. So now basically this dr vector can be described as some component in ei or e1 plus some component of e2 and so on, right? So this components for dr will be dx, dx1, dx2, and so on. So I can write dr vector as dx super I e sub I. Similarly, how I wrote for r, but now we are talking about infinitesimally small position vector, like a very small position vector we are talking about, dr. Okay. So now ds square will be just dr vector dot dr vector. Okay. So this will be the same expression, but there's a d along with it. So what will it be? It will be dx super I e sub I dotted with dx super j e sub j. Now it's a EA and EJ are vectors. So this I can write it, the dx and di are, I mean dx and dxj, so they are just numbers, so I can write it separately, dxi, dxj, into EI dot EJ. Now this thing we know it is the metric tensor GIJ, right? So I can write ds square equal to dxi dxj gij. So this is the expression for the magnitude or the very small displacement or the distance between two neighboring points. So any doubts until now?
Sagar, I think the third metric for cylindrical is also 1 and not Z.
Oh yes, yeah, it is 1. Okay, Sampreet and Anha, did you guys understand this?
Yes.
Until now,
Yes.
Anha?
Yes.
Okay, I'm trusting you guys. So if you don't understand, you can actually ask me. I'll try to explain again. I went little bit fast here because I thought it is simple. But if it is not, you can actually tell me. Okay. So now this metric tensor, basically what it does is it gives you the coefficients for uh, for the displacement. Like this quantity ds is very important for a coordinate system. If you know this quantity ds, basically what our understanding is how to express distance between very two close points. If you know a very two close points, the distance between them, then you can actually extend it and get the distance between any 2 points, right? Now ds square is actually a function of positions, right? So different position, it has different values, isn't it? So this quantity, if you know, then you can find out what all you can find out. You can find out the arc length, right? You can find out the arc length between any 2 points in a curved space. Also, it is used to find out the area between area under a curve, or what you can say surface area. So in every other properties you will encounter this ds. So if you know ds, you can find out so much properties about that curved surface. So for knowing ds, what you want to know, like what you want is the metric tensor gij. So for example, if I want metric tensor, I mean ds square for Cartesian, it is just dx square plus dy square plus dz square. But for polar coordinates, ds square equal to what is ds square for polar coordinates?
dr square plus r square d theta square plus r square sin square theta d phi square.
Yes. So this is the ds square expression in the polar coordinates, right? Or 3D spherical polar coordinates. So it is important. Like this metric tensor is important to get the expression for ds square, where ds square is used to get so many other properties of the curved space. Now, this metric tensor GMN, it is a so GMN is just the component of the metric tensor. So if I say metric tensor as GMN, just understand that it's the component of that metric tensor. Now this component varies as a rank 2 covariant component. So can anyone say what is the behavior of a rank 2 covariant component, like say TMN? So if I change the coordinates, so how will that be related to the original TMN? Like what's the expression? Do you guys remember?
It would be T sub ij dabba xi by dabba x bar m into dabba xj by dabba x bar n.
Okay. I'll write it and tell me if it is agreeing with your equation. So I'll write it to be dou x I by dou x m x bar m dou x j by dou x bar n t I j. Is it correct?
Yep.
Is it correct, guys? Hello. Is this correct?
Could you repeat the question?
Huh?
Could you repeat the question?
So the equation that I have written here, is this correct equation? If you're seeing my screen. Is my screen visible?
Yeah, now it is.
Yes.
Okay. So tell me, is this transformation property correct for a covariant rank to tensor?
Yes.
Okay. So if it's correct, fine. Yeah, it is actually correct. Now, if we show that GMN also varies in a similar fashion, then it behaves as a rank to covariant tensor, right? So how do I show, how will I show that? It's actually an assignment question. I'll try to solve it here. Now, basically, we know that ds square, it's written as dx dxi dxj d okay gij, right? Now when we transform the coordinates, what will happen? ds square remains as it is. It is invariant quantity, right? Every observer agrees upon what the value of ds square is. So if ds square is an invariant, but what will change when we change the coordinate system? It will be dx bar I dx bar j gij bar, right? Now we know how dx changes when we change the coordinate system. We know that any x bar I is a function of x1 x2 x3 and so on, right? So by chain rule we can, or total derivative, by that formula we can write dxi to be how dou I mean xi varies with x1 multiplied with dx1 plus how xi varies with x2 multiplied with dx2 and so on, right? Now this is the expression for a total derivative, right? So I can write it in Einstein summation convention. Dx bar I is equal to dou x bar I by dou x k dxk. So this is a transformation property of what tensor? A rank 1 contravariant tensor. So this shows dx bar I. This component varies as a contravariant component. Now similarly for dx bar j, it is dou x bar j by dou xk multiplied with dou xk, right? Isn't it? Now I'm substituting these two values in here, not here, here, here. Okay. Now we know that ds square is equal to dxi dxj gij. That is also equal to dx bar I dx bar j gij bar, right? So these two are same. So I'll substitute these two, dx bar I dx bar j, by the above expression. So it will be dou x bar I dou x k dxk dou x bar j by dou x. Now I can't write k again, so I'll just write L because I have used k 2 times. So dxl into g bar ij, right? Now what will I get? I can write dxi dxj gij here. Now in the left hand side, I and j is a dumb index, right? So what I'll do is I will write here this value to be dxk, and here I'll write dxl, and down I'll write kl. Fine. Since they're dumb index, I just wrote k and l instead of I and j. Now if you see, I can cancel dxk and dxl, and what I'm left out with gkl is equal to dou x bar I by dou xk dou x bar j by dou xl g bar ij, right? Now I'm not this expression looks more or less like expression for a rank 2 contravariant tensors transformation property, but to get the exact expression, what I'll do is, now what did we assume? We assumed that xi is the old coordinate or original coordinates, and xi bar is the transformed coordinates, right? Now what was the transformation I chose? X bar I is equal to x bar I of x1 x2 and so on. Now this is a transformation that I have chosen, this equation, but for a coordinate transformation there has to be something called as inverse coordinate transformation, right? So inverse coordinate transformation exists for every coordinate transformation. So only if the inverse exists, such a transformation is called as a coordinate transformation, moreover. So because of this inverse coordinate transformation, what I can write? I can write x1 is equal to x1 of x bar 1, x bar 2, so on. Or in generally, I can write xi is equal to xi of as a function of x1, x bar 1, x bar 2, and so on. So because of this inverse coordinate transformation that exists, I can choose x bar I as original and put an inverse coordinate transformation and choose this as transformed. So if you're understanding, like x2 x bar is some coordinate transformation t. I can also write x bar to x as inverse coordinate transform t inverse. So I can write t inverse to be some coordinate transformation, say v. So I can write x bar as old coordinate, some coordinate transformation v gives x. So in this scenario, what happened? x bar became the original coordinate and x became the inverse coordinate. I mean transformed coordinate, sorry. So I can just replace all x bars with x and g bar with g, or anything with bar I can replace with no bar, and anything with no bar I will replace with bar in this equation. Okay. So that, why can I do that? Because of the explanation that I just gave. So if I do that, what will happen? There will be bar here no bar, a bar comes here no bar, a bar comes here, and here no bar. So I just change the bar and non-bar coordinates. So now, is this expression familiar? So this is nothing but the expression for transformation of rank to covariant tensor, right? So you can see that here. So this is how we can prove that Gmn or Gij is a rank to covariant tensor. Now, one help that we can get from rank to covariant tensor is that it helps in raising or lowering index. I'll show you how. Now, let Vm be any contravariant component of a vector, and V sub m be any covariant component of any vector, right? So how can we write V vector as? I can write V vector as V super m E sub m as a vector, right? This you know. Now how can I get contravariant component? So V m is got by dotting V vector with em, right? This gave me contravariant component. So I'll substitute this V vectors expression in this. So I'll get Vm equal to V super m E sub m dotted with E vector m. Okay, I can't use more than 3. So since this is a dummy variable, I'll write it to be n. Fine. Because m was appearing more than 3 times. So now what I can write? I can write Vn En vector dot Em vector. So what is this?
GNM.
Metric tensor.
Anand, can you repeat?
GNM.
Yeah, it has to be Gmn. So I can write V sub m is equal to V super n Gnm. So what is this expression says? I can get a contravariant component Vm by using the metric tensor and sorry. I can get a covariant component by using the contravariant component and metric tensor. So Vm is equal to V1 G1m plus V2 G2m, so on. So I can get V1 by substituting m equal to 1. I can get V2 by substituting m equal to 2, so on. So here so what I can do, if there is any tensor, say Vn, if I multiply it with Gnm, I'll write it to be V sub m. So it helps in raising or lowering the index. So Gnm helps in lowering the index. So when you're doing some calculations, if you want to get a contravariant covariant component, you will just multiply with the suitable GNM on both sides of the equations. So in simplifying the expressions, this property will come in handy. So there is one last topic, that is the inverse metric tensor. So inverse metric tensor. So what is inverse metric tensor? We know that any tensor G has components G11, G12, so on, G21, G22, so on. And these components, how they vary? They vary as rank to covariant tensor. In that manner, they vary, these components. So this is the actual metric. Now inverse metric, I will denote it by G inverse. So how should that components be? I'll just name it like H. Okay. What should this G inverse do? So just when I multiply G inverse with G, I should get the identity matrix. So G into G inverse, I need it to be identity. Now, how is a matrix multiplication? So tensor multiplication is similar to matrix multiplication. So how is this done? We know any matrix A, if it is A11, A12, A21, A22, and some other matrix B is B11, B22, no, B12, B21, B22, right? Now what is AB? AB is A11, B11 plus A12, B21. Right, this is matrix multiplication I'm doing. And this top right value will be A11 into B12 plus A12, B22. And here it will be A21, B11 plus A22, B21. And top, bottom right, it will be A21, B12 plus A22, B22. Right. So if I write AB equal to some C, and if C equal to C11, C12, C21, C22, now what is Cij? So what is this? Okay, just say what is C12 or C11. It is simple. A11, B11 plus A12, B21. Right. So if you notice, okay, I'll take one more. C21. What is C21? Second row, first column. It is A21, B11 plus A22, B21. Right. So if you see 2 and 1, it is appearing here. 2 and 1, 2 and 1. But what is summed over? Summed over is these index. These indexes are summed over. Right. So I can write Cij as a summation of some k a I b, okay, no, a I k b k j, right? This is matrix multiplication. Now in our tensor multiplication, what do we require? we require G into G inverse equal to identity. So if this I call it to be some H, okay. Now, no. So what should this be? It should be delta Ij, right? It should be delta Ij. So why am I writing I in superscript? You will get to know shortly. So basically, when I is equal to j, it should be 1. When I is not equal to j, it should be 0. So that is, it should be like this: 1, 1, 1, and 0 elsewhere. So if the component of the metric tensor is GMN, how should the component of the inverse metric be? It should be of the form some G N K, right? So only then GMN GNK will give me a sort of matrix multiplication expression, isn't it? That's what we got here. But since keeping summing of two lower index is not allowed, it has to be in the superscript nk. So this will give me delta km. So this is sort of a vague proof why inverse metric tensor is a contravariant tensor, but there is a much more substantiate mathematical proof why inverse metric is contravariant. But the contravariant component of a metric tensor is the inverse metric tensor, and the covariant components of metric tensor are the normal components. So if G equal to the components are GMN, then G inverse has components in the contravariant index GMN, such that GMK GKN is equal to delta NM. So how should the contravariant, how should the component of inverse metric be? So the component of inverse metric G should be such that when you multiply the component GKN with covariant component GMK, it should give me delta NM. This condition, if it is holding, then the tensor GKN is called as the inverse metric component. Now, basically, what this inverse metric component does, it helps in getting a covariant component, contravariant component when you know the covariant components. That is, if you know GMN and V sub N, this will give me V super M. But initially, what we wrote, GMN V super N is equal to V sub M. So this is a metric tensor and its inverse helps in raising or lowering index. Any doubts in this? But if you want much more explanation, I will share you guys my notes, okay? So here I have written everything with explanation, and I have derived proofs here. So I'll be putting this PDF in the group and as well as in the website. Go through this. So what all I have done here is neatly written in this PDF. I'll share you guys this PDF. Is it fine?
Yes.
Okay, thank you guys for joining. We'll have a class tomorrow. But before announcing the class, I'll ask everyone who is joining. If there are more number of people, then I'll keep a class tomorrow. Okay.